Today I will be presenting our work on MorphoSys, a system that automatically changes the physical design of distributed database systems. I did this work in collaboration with my colleague Brad and supervisor Kazima. Imagine that you need to set up a distributed database management system. How should you distribute the data among these database nodes or sites? There are two popular techniques, data replication and data partitioning, which I will show next by example. In data replication, we have a master or primary copy of our database and a replica or secondary copy of our database, which we show with lowercase data items. Writes execute at the primary site, while reads execute at the replica site. This architecture is used in the replicated Postgres or MySQL systems. Replication allows the distribution of read load. However, this architecture suffers from a problem. Too many writers executing at the master results in a bottleneck site. Partitioned databases, like HStore or VoltDB, distribute the writable master copies of data among the nodes. In this example, operations accessing A and B go to the first node, while operations accessing C and D go to the second node. This approach avoids the bottleneck site problem we have seen, because both update and read requests are effectively distributed among sites. However, suppose a transaction wants to write data items located on different sites. In that case, we must use a distributed commit protocol, such as two-phase commit, to ensure that the transaction commits atomically across both sites. Such protocols are blocking, and it is well known that they reduce the performance of both distributed and single-site transactions. These two examples show the trade-offs of data replication and partitioning. Moreover, what I have shown are examples of distributed database physical design. We define distributed database physical design as the answer to the following questions for each data item. Which node is the master of the data item? What nodes, if any, have a replica of the data item? And how is the data item grouped with other data items to form a partition, which is the unit of storage within a system? Now I showed you examples of fully replicated and purely partitioned systems. However, a selected physical design, such as the one shown, can be any combination of master placement, replication, and data partitioning. This flexibility allows us to choose alternative physical designs. But we are faced with the question, which physical design should we use? Traditionally, offline tools use knowledge of the workload, such as the set of transactions submitted to the system, to produce a static physical design. But this approach fails if the offline workload no longer reflects the workload executing, which can occur if the workload changes. Workload changes commonly occur due to changes in user behavior over a day or in response to events, such as Black Friday. It would be beneficial for the system's physical design to change to match the workload, as a design that works well for one workload may not work well for another. We aim to address those concerns with MorphoSys, the system we built that automatically chooses a physical design and automatically adapts the physical design based on the workload, all to improve distributed database system performance. Let's now examine the building blocks of automatic physical design in MorphoSys. Let's start with dynamic replication, using a running example with the following data layout. Suppose many clients are reading A. We've seen how replication allows the distribution of read operations. By adding a replica of A on the fly, we distribute the read queries among sites and distribute load. Next, let's look at how by changing the physical design by changing master placement, we can mitigate the coordination overheads from two-phase commit. Consider the update to A and C that required the expensive 2PC. If we dynamically change A's master from the first site to the second site, then the transaction can execute solely at the second site without the need for 2PC. Finally, let's examine how dynamic data partitioning can improve system performance. Suppose there are two clients, both writing partition A, which leads to contention, as both clients contend for resources, such as a partition lock. If the clients are writing to subsets of the partition, A1 and A2, then there is physical contention when there is no logical conflict. So, by splitting the partition to produce A1 and A2, we mitigate this contention. In summary, MorphoSys uses the following physical design change operations to adapt its physical design: dynamic replication by adding or removing replicas, remastering to dynamically change partition mastership, and dynamic partitioning by splitting or merging partitions. There are two key challenges that MorphoSys needs to address to support automatic physical design: executing both transactions and physical design changes efficiently, and deciding which physical design operations to use and when. We make two key insights to execute both transactions and design change operations efficiently. First, we perform all operations at the partition level, so design changes and transactions to independent partitions occur concurrently. Second, we decouple reads and writes to partitions to further minimize conflicts. We proposed a novel partition-based multi-version concurrency control protocol that supports strong session snapshot isolation to support these two goals. More information about this protocol is in our paper. To make design decisions, MorphoSys quantifies the effects of design changes on transaction latency using a learned cost model. As before, consider two clients writing distinct elements in A, which results in contention, and splitting the partition reduces this contention. MorphoSys quantifies the effect of this design change by considering the upfront cost to perform the actual partition split and the expected benefit on transaction latency after the split, resulting from the reduction in contention. For MorphoSys to perform a design change, the expected benefit must outweigh these upfront costs. To compute these values, we decompose all operations into key costs that MorphoSys learns and predicts. For example, the time to acquire a lock or perform a data read or write. We use these costs to predict the change in transaction latency under different physical designs using sampled workload history. To evaluate MorphoSys, we compared it to 3 competitors that use static physical designs and 3 competitors that change one aspect of physical design dynamically. In our YCSB experiment that is write-heavy and has skew, MorphoSys has the highest throughput. MorphoSys has 1.75 times greater throughput than Dynamast and Single Master, and throughput more than 32 times that of VoltDB. To understand MorphoSys's performance, we further examined its physical design decisions. MorphoSys frequently replicates hot partitions to distribute RAID requests and does not replicate cold partitions to reduce space overheads. Hence, MorphoSys uses dynamic replication efficiently to handle skew. MorphoSys dynamically partitions hot data into smaller partitions while grouping cold data together. Doing so mitigates the contention effects without introducing significant overhead. Hence, MorphoSys selects physical designs effectively. We find that MorphoSys adapts its physical design if the workload changes. MorphoSys reduces transaction latency by 60% in the first 30 seconds of this experiment. And when the access skew changes, MorphoSys quickly adapts its physical design without significantly increasing latency. This talk was a summary of our work on MorphoSys, and our paper contains many more technical details, including the formalism of our concurrency control algorithm and its role in efficiently maintaining replicas and how it interacts with each design change operator. The paper also describes how MorphoSys generates design change plans using the learned cost functions and its model of the workload. Finally, the paper contains additional experiments. In conclusion, MorphoSys is a system that automatically changes physical design for distributed databases. MorphoSys executes both transactions and design changes efficiently using partition-level operations. Finally, MorphoSys makes cost-based decisions using a learned cost model. And you can find out more in our paper.